superconductor droplets, we will assume that the uniform distribution surround the airfoil and negligible volume fraction as well as no mass or heat exchange. Next, we will negligible influence on airflow, force considered, and the initial velocity condition from inlet. So this is the governing equation of the airflow. We will use Reynolds average Navier-Stokes equation for airflow on the screen. You can see, and the turbulent model we choose a Calmega. It is because it's based on solution accuracy and computation time. And this turbulent model uses two equations of turbulent kinetic energy K and turbulent dissipation omega to supplement the momentum equation. So next, what is superconductor droplets? Superconductor droplets are the liquid water appear in the cloud at the high altitude, and they must larger than 50 micrometer. As you can see on the screen, smaller than 50 micrometer will be considered as a small droplet, and they will increase the droplet size. Next, we will this project we will use the Euler method. We will have two main methods for the research about the droplets, that is Lagrangian and Eulerian. But for this project, we choose Eulerian, and this Eulerian will consider droplets at the continuous phase using the volume fraction. In contrast, because Lagrangian they consider droplets one by one, not a phase, and we will use in the Cartesian coordinate. We will have four equations because I have 3D wings. As well, the force applies on the wing we will show here. And the difference between the superconductor droplets and small droplets is about the formula calculate the drag coefficient. I will show later. And next, we will talk about the boundary condition for droplets. As you can see on the screen, if we consider the velocity of droplet in VWX multiplied with normal vector, if they are smaller than 0, it means that the droplet is colliding, is hitting into the airfoil surface. In contrast, it means that the droplet move away from airfoil, and we will set the volume fraction to 0 as well as the LWC liquid water content. Next, this is the characteristic of the superconductor droplet. That's the deformation and breakup. As you know, when the superconductor droplet move in the air, and when the Weber number larger than 12, they will break into the smaller droplets. And this is the big difference between the superconductor droplet and small droplet. About the drag coefficient formula, we will consider two main kind shape of superconductor droplet, a disc and sphere. And this is the formula to calculate it based on the Weber number. Next, the drag coefficient in disc and drag coefficient of sphere, the formula shown here to calculate, and final is the weighting function. Next, this is also one of the characteristics of superconductor droplet in the splashing. When droplets hitting to the airfoil, they will splashing and rebound to the air. And as you can see, that we have three main splashing model because using phase eyes, that's the Mundo, Honsek, and Wright. Mundo is splashing model, but they don't use the angle to calculate the direction of velocity of droplet. So within three splashing model, I have the comparison between them. As you can see on the screen, that's about the Wright, the Honsek, and Mundo. So about the accuracy of Wright splashing model, we choose Wright splashing model for our project. So next, this is the two main parameters we will consider in our project. First will be the pressure coefficient, and next will local collection efficiency beta. And as you can see on the screen, this is the formula for CD, and the local coefficient efficiency is the probability that the particle approaching specific location, and this will be equal to the multiply on the surface divided by component on the far field. So we have two airfoil model. As you can see on the screen, this is for 2D and this is for 3D. And the reason why we choose this model because the modern application. As we add for NACA 6 series, this is represented for real aircraft. They will fly in the real condition, and it's easy for our to validate with the real aircraft. And next, we will come to the first case when we 2D. And for 2D, we have two kinds of grid, all grid and C grid. But this we do the C type grid for selected for this study, and we divide this mesh surrounding this, and this is battery condition for airflow. And now we will come to the inlet condition for 2D. This is inlet condition following the NASA reports about this airfoil, and then we will validate the pressure coefficient. As you can see on the screen, the pressure coefficient do not have so many difference between our experiment and nature report. And this is the contour of pressure coefficient. As well, we also validate the collection efficiency of this airfoil at two angles of attack, 0 and 6 degrees. Next, with my project, I will check the result in three cases. First case is I will change the medium volume diameter condition. Case 2, I will change the angle of attack. And case 3, I will change the Mach number to see the difference between the condition for droplets. So come to the first case. As you can see on the screen, if the medium volume diameter increase, it's also the beta collection efficiency also increase. This is for 0, 4 degree and 8 degree. And you can see clearly on the contour that with the higher volume diameter, this will have the higher range for data for collection efficiency on the airfoil surface. And this is for 2D wings. Next, we will change the angle of attack. If you see that with the increased angle of attack, the more droplets will hitting on the lower surface of airfoil. And then we will see the Mach number. With the higher Mach number, this means with higher velocity, it will have the impact more. And as you can see on the green, that's the higher collection efficiency will collide to the airfoil surface. Then we will come to the 3D wings. This is the NACA 6 series, one of the popular NACA for commercial aircraft. And I also use C-grid for this airfoil. But it is different because I have the mesh surrounding the airfoil surface. As you can see the battery condition. And for 3D wings, this is the grid on surface 3D wing. And this I will use this section airfoil for testing because I am based on the NASA report. And I choose this section airfoil. I will cut it and check the data. So also this is the inlet condition for NACA 6 series. And this is pressure coefficient invalidated. As you can see, we have a small difference at the tail of aircraft. This is for collection efficiency. And come to the case for this is also similar to the 2D model. I will also change the MVD, angle of attack, and Mach number to see the difference between them. And it shows the same change that with the higher medium volume diameter, we will higher collection efficiency on the airfoil surface. As you can see there, with the yellow line will be the biggest volume diameter will be equal to 200 micrometer. And this is the contour. You can see that the difference between them. And this is angle of attack. It shows the same strength because you see if the angle of attack change, the more droplets will hit into the lower surface of airfoil. And this is symmetric airfoil. So at the 0 angle of attack, we will see the symmetric graph between the highlight point. And this is for Mach number. It's also increased with the increase of Mach number. And finally, what we find in this project, we over study about the superconductor droplets, theory study about the two-phase flow, development of computational model, and numerical method, analysis of main parameter influence. And if we go further, I can research about something about the icing prediction, integration and collaboration with other research. I'm also a special thank to Dr. Trần Tiếng Anh and Dr. Yun Tai for their support during the development of my project. Deep gratitude to Board Director of Ho Chi Minh City University of Technology and Aerospace Engineering Department for supporting my time studying at the school. This is my reference for my project. Thank you for your attention. That's all I want to say today.
Okay, you said 3 minutes of the time limit, but it's okay. I would like to invite Mr. Long to read the supervisor's comment first. And then Professor Nam will give you some comments as reviewer of the report.
Thank you, Professor Lee. So now I would like to read the assessment form for custom project of looking at some comments on the strong role or advantage of the report. The report will be structured and present scientific investigation of successful progress focusing on a hard wind. The plan and industry standard safely to assist ICM and use effectively with clear explanation of numerical methods. The result validates again NASA is built for data, increasing the level of the fine. The study explored K parameter, property side, angle of attack, and back number in detail. Some comments on the shortcoming to improve careful rules will be needed to correct minor language and formatting errors. Adding more data visualization of study, illustrating the application aspect. The supervisor is no question for me.
Yes.
The overall assessment, 8.9.
Thank you, Professor Long. I'd like to invite Professor Nam to read some comments.
Yes. So I just read the comments. Okay. The physics has been written carelessly and has unreasonable structure. So the student needs to revise and edit the physics. The student must ask the governing equations for the simulation, remove the figures that do not present the simulated result of the physics. The student remember the first part of the physics in Roman numeral. Revise chapter 1 and 5 according to the structure of a physics, not the outline of a scientific research topic. The student only present the turbulent model used in the physics and does not present the irrelevant turbulent models. Present how to set up the simulation problem with the appropriate for recognition and computation domain. Review the analysis of the research in chapter 4. Many figures are shown but not mentioned in the comments and description. The student needs to revise this part and analyze the research more carefully. The current analysis of the research is too sketchy. Math independent of the simulation must be asked to the physics. The episode should closely control the student physics rewriting and editing process to improve the physics. So 3 questions.
Do you have notes? Please take notes.
why must we analyze the data faster during the ice acquisition? In the figures, the NVD parameter increased by two times from 94 micrometer to 200 micrometer, and the mass number from the 0.25 to 0.8. But there are no significant difference in the faster data. The Icelandic from the survey of the third question from the survey of the parameters such as AOA, mass, and MVD, and observation of the simulation result, which parameter affects the factor data the most?
So now we will answer.
Yes.
With the first questions, associate professor asked me that why must we analyze it, the beta coefficient before predict ice? Because that the beta coefficient for the prediction of ice of the ability of droplets hitting on the surface. And with the high collection efficiency, the data is not only the element affecting the icing. About the icing, we have shown in three stages. First, we saw the air phase. Second is water, and the final we will calculate the ice formation. And if the data collection is from this state, it just used to predict where the collection efficiency concentrates so much, and it will combine with all the elements like temperature. Because if collection efficiency higher, but the temperature of the airfoil is not enough, or the temperature is high, it will not have the icing on that. And also, if the temperature is enough for the droplets, it will have the icing immediately. But if not, it will have formation of ice gradually. It will collect and have the ice surrounding the airfoil. So the beta, we need to survey the beta to predict the ice formation, not the ice shape or not the aerodynamic performance. We just use data for predict the ice formation, about the ability of ice on the airfoil surface. So with the question number 2, why the NVD is higher than 200 micrometer compared to 94 micrometer? But why we don't have the collection efficiency too different? Because we have this formula. As you can see on the screen, this is the formula to calculate the number of droplets in the air phase. So if you see that, if all this reduce constant, and with the increase of NVD, it will negative with the number of droplets. So that means with the droplet higher, it will have the less number of droplets colliding to the airfoil compared to the small droplet. We will have more droplets in the air collide to the airfoil. So this is cause the unbalance, not significant difference of this. It's just small because we see the formula. These two parameter is not the same. It's not increase and all the increase. It's in contrast. So with the third question, from the surveys of 0.8 Mach and which parameter affect the beta the most, I suggest that will be the medium volume diameter NVD, because in the formula calculate the beta coefficient, we will have the effect of MVD on the formula. So this will affect the most. But with the velocity or different angle of attack, it just see how the droplets hitting to the F4 surface on upper or lower surface.
For the first question, the beta factors so will affect to the eye shapes. It's not the eye information because when you look at your picture, then you will see you will predict the eye shape from here. If the maximum value of the beta, and then you will have the maximum nest of eyes.
Yes, but I want to make clear that my project is just start at the water phase. We not come to the eye. So if we need to ask, we need a other factor like temperatures, and we do not come to the ice phase. So we do not have temperature. So it's just a prediction for ice, not.
Yes, but you need to understand the ice, the whole ice accretion process, and then so you can list this as the future work in the young process.
Here, my future work, I say conditions.
So the first question. So you confirm the NVDs will affect the first data the most, right?
Yes, in three parameters, I suggest that NVD will affect the most between the velocity and the angle of attack. Yes, I think the NVD will affect the most. The change of angle of attack, just we see that the upper surface and lower surface, which will have the more droplets hitting on it.
I think so. AOS will also affect.
Yes, because with higher angle of attack, we will have the lower beta collection efficiency on the F4 surface.
Yes.
So I have two questions for you. If we go back to slide 20. Here, could you tell me why you choose the values, for example, K1, not for 150 and 200, and K similar that to K2, 0, 4, 8, 1?
First of all, I will come to the case one. The reason why I start from 94 because if in the definition they say that the supercooled droplet just needs to greater than 50 micrometer, but in fact, with this diameter, they still consider droplet as a smaller one. In the reality, with the droplet greater than 90 micrometer, they will consider as a supercooled droplet and have the equation of supercooled droplet and the phenomena. So I start from 94 because this is the from NASA experiment. I take the first case from NASA to validate and also my results. Then I will increase to 100 and 200 because that's if I choose smaller one like 100 or 100 and ask the associate professor Lê Tống Phương Nam asked me that why the bigger 200 compared to 94 is double times, but it has still the not significant difference between the beta parameter. So that's the reason why I choose I multiple two times to see the difference between them because the MVD because the liquid water content will remain the same. So I choose the 94, 150 and 200. And for the case 2 angle of attack, the reason why I choose 4, 2, 0, 4 and 8 That's based on the next experiment also. First, I will validate with 0, 4, and 8 angle attack for my correct of my model, and then I will change the angle attack to see the difference between them, and that reason why I choose that parameter.
So next slide.
Next.
I see you consider the every conditions, so you change the value of every conditions. So you don't need to change every condition and technical.
Sorry, this is just a more case, like this is 0 angle attack for different MVD, and this is for the 4 degree for different MVD. I'm not changing that.
You can compare two cases different values. Your contact angle 0 and the false. You just keep, if you want to compare the effect of the table, keep maintain every conditions.
Yes.
And then you can analyze or give a decision.
Yes.
You know?
Yeah, I know.
You change two effects, we cannot give a decision.
Yeah.
It's not really. You just keep
focus on.
Yeah, keep on content.
Yes.
And the way okay, you IRC you already consider the effect of content.
Yes.
Understand what I mean?
Yeah, I know that because this I just do more to
No, no, no.
yes, thank you, sir.
Okay. Okay, I have separate questions just to understand your work. So, what do you mean by distance from the highlight?
Distance from the highlight means that's when the data from the software when I export to outside, and this is the F4 steps. That's the collection efficiency will distribute all of the F1 surface from this. So we take the highlight from this to survey, and we just survey.
The highlight. What do you mean by highlight?
Highlight
Is
point.
there any definition of that kind of highlight? Do you have some sketch or image or pictures that show the highlight?
Highlight point is mean that at the 0 angle attack we have the highest efficient collection efficiencies. So that's we will check this and we will survey from 200 millimeter of the upper surface to 200 millimeter of the lower surface to survey the collection efficiency. Because if we survey all of this, we don't have any to ensure that I'm correct. Because follow to the article, we just have we just survey from here to here, and this is also the place the super cool large droplets will hitting on it. And we will survey more here because if the super cool large droplets attack on this, the normal vector will be in contrast, and this means that they move away from the F1, so we do not have anything. And as you can see on the screen, if we expand it with 0 over here, so we focus on the highlight point to 200 and.
That means the highlight point. This is a reference, and this is a reference case by case.
Yes.
This is not just a fixed reference for a given airfoil. That means that highlight will change with angle of attack, right?
Yes.
Because this is the highlight means the points with maximum hitting particle, right? So that kind of highlight will change from when you consider different angle of attack. For example, you choose different reference that means different highlight. Am I right? And do I understand that correctly?
Yes.
You choose different
Sorry.
highlight means reference. Highlight for your case is reference. Right?
Yes, it means that if the angle attack here, the highlight point will be also the highest here, so it's like this. So this is the highlights compared to this. if the collection efficiency here is high, so I will choose.
That means for each simulation, you have to figure out, you have to identify
Yes.
exactly the position of
The highlight point.
a highlight point.
Yes.
Is there any information in your report that you present the details, that means the position of that highlight for all of your simulations?
Currently I am not asking the definition of highlight points because in NASA report they don't mention about that, but that we understand about the highlight point from our experience and my advisors.
Because I find that your results depends a lot on the highlights, because this is a reference.
Yes.
All of your results logged based on the highlight.
Yes.
And if you miss that clarification in the report, it's hard for the readers to follow what you are doing.
Yes, I will understand.
Okay, so as I understand that you state your study stem from the NASA report based on two experimental study of 2D airfoil and 3D airfoil.
Yes.
Then you develop your study by changing the variables like angle of attack and Mach number.
And medium
Okay,
voltage.
can you go back to the validation phase?
For 2D or 3D?
Yes, 2D first, for example.
For
This is
pressure
for
coefficient.
2D. So NASA did experimental study for this NLF 04, 14, airfoil at 2 angle of attack
Yes.
and Mach number. What is the Mach number of the experiment and the Mach number you are doing the validation?
The Mach number I will in this I will change to the flight speed. So for easy because they in the report they use this and
You
this.
do the same thing.
Yes, I do the same thing.
Okay,
All
flight
setup.
speed, here, do you estimate that what is the Mach number? If you have to estimate the Mach number here,
It's really equal to my first game. It's really 0.25.
okay, 0.25. Then your contribution is that you continue with this study by changing the angle of attack and changing the Mach number.
Yes.
Right? Okay, so
As well, volume time is one of the most significant.
so there are a lot of a great number of variables. MPD,
NVD angle attack,
angle of attack, and
Mach number.
Mach number. And then you continue with a 3D case.
Yes.
Right. Okay. So what is the computational cost when you do the 2D and 3D airfoil?
Yes, this is a significant problem because that's with 2D we just need to. This is also the reason why I choose Eulerian method instead of Lagrangian. With the Lagrangian, then we consider droplets after one by one droplets, and this will hit the airfoil. But with the Eulerian method, then we consider water at the continuous phase, and if for 2D winds, we can do with the droplets like this, and it's not need too many time to do this, too much time to do this, but with the 3D winds, it's not so many computational resources, the time to calculate it, and but if we can do or not, yes we can do, but we don't have enough time, resources or computer or anything to calculate it. So we choose to use Eulerian method to calculate it to conserve our time and save my time and my resources, and it's suitable. As you can see that the validation is not have so many different because the NASA use Lewis they use the Lagrangian method, which calculate one by one droplets, and this need to have more resources to calculate it. So I choose Eulerian, but we have the same result as the Lagrangian.
Yeah, but you didn't answer my questions. The computational cost for 2D and 3D, because you did 3D case as well in the report. So what is the computational cost when you do the Eulerian method for the water drop for 2D and 3D? Because you carry out two different studies, a certain air voice for 2Ds and another air voice, another case which is 3D view. Okay, share with us the computational cost when you did 2D simulation and 3D simulation in your setup.
I want to make clear that computational cost. This means you want to know the
Mesh structures,
computational
computational
time.
mesh structures, for example. What is the mesh structures for 2D and mesh structures for 3Ds, and how long do you need to run your simulation until it converges?
First of all, for 2D airfoil, the method approximately is 1 million, 1 million cells. 1 million cells, and for every case, and this because I do face up eyes software, so and this deliver
What's
this
the
can
name of the software?
face up eyes. It's from the ANSYS software.
Yes, this
It's
is
one,
ANSYS, right? This is
but it's one of the software in ANSYS platform. So
this is free for this is included in the
Yeah.
student version. Of
yeah, it
ANSYS.
has student version, and I run by student version. And with this one case, I did when because runs airframes for airframes of 2D, and this about 4 hours for airframes 2D, and 1 hour for water phase. But with 3D, it's harder because for 3D, as you can see that I'm not just expand, I messing all of the wing like this, and this in the box, and this in the box. So when I put it in the software, I need to many times like 8 hours for one case for airframes, and I have 2 hours for water phase. And with this, I cannot run by my laptop. I need to run by the computer on the table because it needs more resources. It needs more RAM, more V to run it, and the cell for it is equal to 4 million cells. And
Kevin, how many cores?
I mean, what?
Processor.
I need for 3, I need 6 cores. And for it's just I use whole of my computer for 4 cores to run 2D. 2D is more simpler, but it needs more time. Also this time.
Okay, thank you. Next question, and final question. So you consider 3 Mach number
Yes.
from low speed to high speed, 0.8.
Yes.
For these 2 cases, for 2D and 3D, right?
Yes.
So what is the motivation of Mach number of compressibility effects in icing formations? And during your study, at the end of your study, can you state, can you give some remarks about compressibility effects on ice formation in these 2D and 3D cases?
Yes, but I need to make clear that about the icing program. I want to make clear that about the icing program, we have 3 main phases. First, we will solve the air phase. Next, we will solve the water phase. And finally, we will solve the ice. So, my project is just stop at air and water. We do not counter the ice, and we do not calculate the aerodynamic parameter on the eye. So we calculate it just to predict the eye shape of the airfoil, as Associate Professor reminded me before. So that's the reason why I not mention anything related to
Okay, I agree. So what is the compressibility effects? For example, just compare these two cases, Mach 0.2 and Mach 0.8. What are the difference? What are the difference and the effects of Mach number in your process, in your result?
The Mach number is my result. That's if you see that if this is for tuning, so if the Mach number increase, we will higher parameter, we will higher condenser efficiencies on the endpoint surface. That means if the higher velocity, that region, we will have higher ice information on it.
Not much. There's not much difference between 0.8 and 0.2.
Yes.
We can say insignificant effect of Mach number in your study.
Yes,
Does
sir.
that make sense? So
But
that means in the reference published data, can you find any relevant study with high Mach number, for example, at these airports?
No, they don't do that. And this is the new case I prefer to do because although it's not too many different, but you know that the upper surface and lower surface they have the broader collection efficiency on that. It also affects because when fly at the high altitude, they also affect something that that's the difference between the high velocity compared to the small to the low velocity.
I think that the simulation setup for very low speed and high speed, Mach 0.8, should be carried out with some consideration, because from your results, even in 2D or 3D, compressibility effects is not quite significant.
Yes.
Because you study air phase and water phase. Air phase at low speed and air phase at high speed, as you have learned in aerodynamics, they are different, right? There's some kind of similarity with corrections for incompressible and incompressible case, but I think in this case it should be analyzed with care because you cannot compare your results at high Mach number, because in other case they study only very low speed at Mach 0.2, and you develop, you do more simulation at Mach 0.8. I believe that simulation setup for Mach 0.8 and Mach 0.2 should be different, because for air is incompressible and for compressible air. But here the result seems similar.
Teacher, can I explain it?
Yeah.
Because we assume that the water phase don't affect the air phase. So it means that two independent phase, air and water. So this means that we just take the inlet velocity of the air phase for water. We not take the characteristic of air phase water. It's only just it's the independent phase. It's not affect together. So the reason why the increase of Mach number, we don't have so many difference between the collection efficiency.
Thank you for your